I'm Goma from National University of Singapore, and today I'm going to talk about the dynamic scheduling on video transcoding for Dash in the cloud environment. So here's an outline of my presentation. The first thing I would like to talk why we want to use Dash. So the first thing is nowadays everybody try to access online videos using some mobile devices instead of the PC, this kind of thing. And the different mobile devices might use different resolution and different size of screen. So we need to provide multiple copies of the same video to encode it into different bit rates, into different resolution. Another concern is about the variance of bandwidth. So even if you use the same device, you probably need to meet the different condition that the bandwidth is changed. So we do some data collection around Singapore. So here's the map of Singapore. So we try to collect the bandwidth of some place, and then we do some interpolation between the collecting point, and we also smooth the curve. So another
is that wireless bandwidth?
Yeah, wireless bandwidth. Another one is that we collect in the same place inside the NUS campus, but with different time. So you can see that also the wireless bandwidth changed a lot. So what my paper concern is about from the server side, how to prepare the different copies of the video segments. So we need to provide multiple copies for the same video segment for streaming purpose. So another thing is why we want to use it in the cloud. So nowadays, according to one of the YouTube statistics, that mobile makes up almost 40% of YouTube global watch time. Another thing is about for the single machine or single PC, it has quite limited computational capacity. So we need to use in the cloud to make the video transcoding service. So here's our objectives. So we want to, the thing I want to emphasize that my research focus is on how can we achieve the best performance with the limited computational resources. You know, so nowadays we have a lot of cloud service for the Amazon EC2 or the rack space, this kind of thing. They also provide for the video transcoding service, but it will you need to pay money for that. And if you have as many machines as you require, then you can do everything. But with very limited resources, how we can achieve the best performance. I think there's not too many researches on this. So our objective is to first to minimize the video computation time after the video is uploaded to the server, and second thing is to try to balance the workload with the amount of processors. And then we want to support the near live streaming of video events, and then provide the smooth video playback. So the basic idea is we try to maintain two queues in the cloud server, and then we can distribute the free processor that to run the jobs that are not under request and just for the job task upload video to the server. And the other thing is that when the video is just upload to the server and then it requires immediately, we have to find the fast processor to run the jobs to make the video available as soon as possible. So here we do the first method. We're using the video transcoding time estimation to help us to model the scheduler and also find the fast processor. So here we do some statistics using different processors with the same configuration. We have about 11,000 video segments that are collected using the Android devices. So the original bit rate is 2 megabytes per second, and with the resolution for 720 multiplied 480. Then we have two target bit rates. One is 768 and the other one is 256. So here's the statistics. We got the dot points for both transcoding the original video segment to medium bitrate and lower bitrate, then we'll get for each individual section, we got the video transcoding time. And then we draw like fitting curve for both these two bitrates. And we want to like build a model to calculate the video transcoding time and estimate the video transcoding time according to respect to the video duration. So the fitting curve is like this, shows like this. So the actual video transcoding time we estimate is the value we calculate plus some error. So you can see from this figure there's a lot of like bias compared to the fitting curve. And then we do some statistics to try to like build another model to see whether the error between the calculated value and the actual values follow some distribution. So we can find for most of the case it follows a gamma distribution with some like coordinates coefficients. Then we do some like the video scheduling according to the VTD estimation. So here's like a basic framework of our system. So the mobile user will upload videos to the web interface, and the web interface will like forward the transcode, forward the job to the on the top to make the video transcoding service. And then if another, like the mobile client, the user will try to send some video watching request to service. The video is ready, then we directly like send the HTML address, HTTP address for the like video sending to the mobile client for streaming. If it's not, the video is not ready, then we may send the like the job from here. We will have two queues. From here to make it as a like urgent job. So I'll show you some. So the idea is that we maintain two queues here. We call it NQ and TQ. So NQ is that job are not under watching request. So we use the like the shortest job first scheduling, and then if the job is under watching request, then we consider it as an urgent job. Then we can like do some like deadline first and assign the enough but not redundant processors to run job. So here's a method how we can like calculate the job deadline. So the LVA is a kind of pre-fetching or pre-buffering of time of the video streaming. So when you like watching some videos in YouTube, you always have like 15 seconds advertisement. So we consider about this with like LVE, and then it's kind of calculate. We calculate the previous cumulative video duration of the segments. Then this is considered as the summary, sum as the job deadline. And then here we want to calculate about how many processors is enough to assign to the like running the urgent job to the that can meet the requirement of the urgent job so that we can achieve smooth playback. So I'll show you some examples. So initially we have PQ is empty and we have NQ for the normal upload videos. So then this is solved by the like shorted job first. Then when like video B1, the segment B1 is requested by the client, then we remove all the following segments from the video B1 to the PQ here. So then here is not sorted by the short job first, but only by the like video ID. So we assume that people usually like to watch the video one segment by one segment, not jump forward and backward. Then if another like video requirement starting from like DM assigned to the like server, then we can like reorganize the queue, job queue here in the PQ to organize this, achieve this one. So the thing we want to do in the server is that we want to monitoring the video transcoding time on each of the processors, so that we by compare the estimate VTT and actual VTT, so that we can have a basic idea that which processors is the fastest one, and we can use this the fastest processor to run the urgent job. Another thing is that so at the beginning, if we have enough processors to run the job, so we can run the video transcoding manner as 0. So we have so in my current system configuration, we have 5 video transcoding minors. The 0 means that we can transcode from the original video. We transcode both medium bitrate and low bitrate together. But I'll show some detail about how this is configured later. And then if there's not enough configuration nodes, then we do some the VTM switch to make to do the smooth playback. So here's some. I'll show some experiment results. So the evaluation metric is about we count about startup latency, the number of the quality switch, number of the rebuffering events, and the mean rebuffering time. Then we calculate the mean option score here. And we'll also consider about the load balancing among the processors. So here's some the configuration. We generate 3 streams to see how the schedule works under different workload. And we generate the mean interval time is 5 seconds. Here's the video transcode miner. So the 0 means transcode low and medium bitrate together. And then 1 is first low, then medium, and we go 3 and 4. So totally, we generally have 5 transcoding miner. So here's I show you the scenario 1 is about there's no video watching required, so we just want to test in the different workload how the schedule performance. So here's the maximum value for the concurrent request is uploading is 6, and we can see from here the queuing time is quite low, and also the completion time is not that high. So we probably will notice in this part the queuing time is quite low, but so the computation time is high. So what I found from my experiment is that it depends on the individual transcoding time of the segment. So you will see in the next 2 streams also for the same part of the video, same part of segment. This one is the queuing time is not that high, but the completion time is high. So stream 2 is about we try to upload the streamline 6 segments per second, and stream 2 is 7. So when you see when it reaches 7, the queuing time also start to increase. That means that it will reach the maximum capacity of the system. And then also for the completion time it grows. And for 8, it grows sharply. So we can infer that in the current system configuration, so we can only support about 6 or 7 video segments upload per second. Then we also count the load balancing about the stream 2. So you can see we have 25 processors, and the overall video transcoding time is almost the same with small variation. And we can also calculate the mean normalized VTT. So the normalized VTT is compared between the actual VTT with respect to the video duration. You can find that for different processors, the transcode, so the speed of the different processors for transcoding is different. So for scenario 2, the videos are under spec for watching while they are being uploaded to the server. So I will show you 3 experiment results. So the first one, we vary the different LED, so which you can think about it as like the length of the advertisement before you're watching TV, watching video. So you can see from this, the MOI has changed, and we got, so for some of the case, when you got 10 seconds for LED, we got a better MOS, but for some of the case, the buffering time at the beginning is longer. So this one is better. So I'll show you you can see from here. In this case, when we set the LED at 10 seconds, you see a lot of get this. We got one time of the quality switch and 3 times of rebuffering event. So I'll show you for this case for some other experiments. So here's a comparison between the video transcoding time in both the NQ. So NQ is NQ is for some normal upload video segments. And then we have 5 clients to generate video watching requests. The arrival time is different. So the first one is arrived. For client 1 is about from here. So you can see that at the beginning there's no video watching request. The average VTT for the NQ is around 2.5 to 3 seconds. And then after the first video watching request arrives, the VTT, average VTT grows up to about 4. And then after we got more video watching requests, it grows up, and then when the request finish, and we then jump back to some normal level. And you will see another observation is that for most of the case, for both of them, we have the 5 clients. We have 5 different watching requests, and you can find that the 5 is the faster processor to run. So the average of the VTT for both 5 clients is 5 clients are almost smaller than the average VTT in NQ. So here's another one. Another one I want to show about the comparison between timeline and the computation time for client 2. We also under the same some condition about this configuration. So the LED equals to 10 seconds. So the timeline about the client 2 is shows as this red line. And in fact, when the actual transcoding video computation time reach this value, we do have a quality switch to the client. And then for the if we don't have the video transcoding minus switch, I'll keep transcoding to the medium bit and low bit together. We can then arrive for it will be another 3 rebuffering events here. So when the segment is finishing, the transcoding is finishing after the previous segment playback, so it will have some rebuffering events. Then the users need to wait until the segment is downloaded from the server. And if we have the VTM switch, then we just transcode the segment required by the client. Then it will decrease the video computing time. So from the user side, he will achieve the smooth playback and will not waiting anymore. Here's some conclusions. So we propose the video transcoding estimation model recording using some statistical method, and which is with respect to the video duration. And then we can, from some experiment, we can prove that the scheduler can dynamically distribute video transcoding jobs according to the VTT estimation and also according to the system workload. So we can find the fastest processor to run video transcoding job. And then we have the the scheduler can also dynamically serve the request and adjust video transcoding mode accordingly. Okay. Okay, here it is. All right.
Any questions?
Can you get back to the slide where you show the equation, how you compute the BTT? Yeah, just record this. Yeah, come back. Yeah, this one.
Yes.
No, this MOS actually. No.
MOS.
MOS. Not
MOS.
Okay.
This one?
Before. Yeah, this one, yeah. How did you pick the parameters, the coefficients, 4, 2, 3, based on which side?
Sorry? You mean for this one?
Yeah.
Okay, so this for the MS formulation, I got some from the other Russian paper from more character.
Okay. Okay, so based on another set. Now, second question, which is most important for me, can you move to the next slide?
This one?
Yeah, this one.
This one.
So basically, in case of live streaming, basically, chunk duration is around 2 seconds. All right. And as far as I see, latency there to transcode one chunk makes a lot of seconds actually. It even exceeds the length, the duration of one chunk. You see? So for instance, when I see chunks
You mean here?
on the y-axis latency.
Latency.
Yeah.
Okay.
So this latency, the time you spend to transcode one chunk, isn't it?
Yes. So from the calculated latency means that when the video is uploaded to server, it starts to calculate, and until it's finished, until the segment is finished transcoding.
Yeah.
So it calculates the latency.
So it finished transcoding after 5 seconds, 10 seconds, something like that?
Yes. So this is because we don't have the version job, so we just want to at the same time transcode the original upload video to as many possible bit rates together.
Okay.
So it means so for our case we have some processing nodes, and then we transcode the original uploading segment to both the medium bit rate and the lower bit term together. So it will have some time. Now, so also this time including the processing node to transcode from transcode the video upload segment from the research storage repository to the processing node. And if I think if there's no video watching request issue, and the processor will run it in the back end, and nobody is watching immediately, that will be not key issue. But if, as I said, if we have video watching request, then we need to transcode the job as soon as possible. So, for a point, it's too long.
Yeah. It seems that it takes one time to transcode one chunk, one content, isn't it?
Yeah, we have.
Occasionally live streaming when people are watching contents on live. I think spending a lot of time transcoding may generate some bad user experience, since they will experience some delay. So this may mean.
Okay. So when you think about the problem you mentioned, so we have some if it's for the live streaming, we have to. So if the people are uploading the video, then so for live streaming we can consider that some people are watching, right? So then it's like the second scenario. We have some video watching request. Then I think it's about the latency about maybe 1 to 1.5 seconds. But I think it's probably okay.
Yeah, that's easy.
Another question?
Yeah.
Sir?
What kind of video did you take for your estimation, for your VTT? I mean, did you try different kind of videos like sports, movies, cartoons?
Yes, for the sightseeing videos, we take like the Android phone around Singapore, so like the Marina Bay area for some like famous landmark, this kind of thing, so people can, as they taking some tour, and then tour and on bus, or they can just walk around and take this kind of video. And we, the video seconds are like we do is the segment. The video is segment from the mobile client, and 5 seconds segment or something like less than 5 seconds segment then upload to the server. So the data set we use is this kind of data type. So for we got most of the video segment. The last of the video segment is 5 seconds or something like that.
Yes, sir.
What kind of CPU did you use? I mean, transcoding time is highly dependent on the performance of the CPU.
Mm-hmm. Yeah, in the experiment we used the Intel Xeon CPU. I don't remember the exact number, the frequency, but it's a 4-core CPU. It's around, I think it's around 2.2 gigahertz.
Did you consider any heterogeneous CPUs on your machine?
Right?
Heterogeneous CPUs?
No.
Only one CPU for every machine?
Yeah, only one CPU and 4 cores. And for each CPU has 4 cores. Yeah, actually we during the experiment we do some. I did have some do some experiment with like multiple CPUs in the server, but it's not the. I think it's quite the situation is quite similar, but then the result is not recorded in this paper.
So if many requests can be processed by one node, I guess that the scheduling algorithm in the operating system may affect the transcoding time too. So did you consider all this?
So far I didn't consider about this. I think it's a good point.
Any other questions? I have one actually. So, you talk about this work within a Dash framework. Dash requires some sort of manifest file generation and then sending that information to the client, and then the client asks for video segments accordingly. So there's also some delay involved in manifest generation, and then that pulling of that manifest by the client, and then making the request based on the manifest by the client side. So actually, when you are doing all this transcoding work, and if you're changing the segment duration, or changing the segment, some segment related information on the fly, that means that you need to refresh this manifest information periodically, maybe very frequently. That might play into your game from the opposite direction, meaning that it might actually increase the delays further than you anticipated, because now you need to generate the manifest, and then you need to somehow let the client know about this manifest change, and then the client is going to do the new manifest and then make a new request. So so frequent changes in your system might actually be a negative score for your application. You need to think about this. I'm not sure at this point whether it makes a huge difference or not. That's certainly one thing that you should consider.
Yeah, thank you for your comments. Yeah, actually for this one, I also have some consideration about. So at the beginning we have like test for the classical time to this kind of estimation, and then I know that for if you run the experiment on the private service in like a shared system, maybe other object type size for the object type for the CPU resource and memory resource. And then we do actually when I try to find the fastest processor, it's kind of like compare the what we estimate the time and what actual time. So it's kind of hard to realize that this maybe the CPU, 20% of CPU or memory is used by some other thread. Yeah, I know this, yes, after probably maybe few days or run of the system, we have to like recalculate or remodeling the whole system. We do something to avoid this kind of season. Still, yeah, I think probably we need to do some like self-tuning.
Right, yeah. All right, let's thank the speaker again. This is the end of